my name is Vinayak from Maya HTT. In this video, I will show you how to perform a random-based excitation simulation by using SimCenter 3D Response Dynamics. Random-based excitation testing is prevalent in the space, automotive, and electronics industries. We will be using a random-based excitation event to simulate the random response of a medium-sized spacecraft model. This new event dramatically reduces solution time while increasing results accuracy. It is more than 100 times faster than the competition. We will excite the spacecraft in the lateral direction by using a notched acceleration power spectral density function. We will review the output peak acceleration and margin of safety contour plots, as well as the power spectral density response function plots. Let's begin by opening the simulation file. Here you can see the spacecraft assembly consisting of the bus, the various payloads, as well as the launch vehicle adapter, the lower interface of which is fully constrained. The FEM of the spacecraft contains about 130,000 1D, 2D, and 3D elements, pointing to both metallic and composite materials, and about 160,000 nodes. As you can see from the simulation navigator, this simulation part already contains a SimCenter Nastran Sol 103 response dynamic solution, which will be used to calculate the mode shapes of the structure. Edit the solution and define the purpose of the solution to be the downstream definition of a random-based excitation event. Material strengths and stress limits will be used in the solution. Additional laminate failure theories are supported. Then edit the dynamic subcase and define some residual vectors to improve the accuracy of the random solution. Create a modeling object and disable all of the options except for the inertial relief load. Next, solve the solution. Once the solution has completed, define a new response dynamics meta solution. By default, the solved Nastran solution is selected. We can see that 6 residual vectors and 35 normal modes have been calculated. Let's now assign a 2% viscous damping ratio to all the normal modes. Now let's create a new random-based excitation event. Engineers often hand multiply root mean square random results to obtain the 3 sigma responses which are typically required in the space industry. Since the random-based excitation event computes peak results that correspond to the desired confidence level, this tedious manual step is no longer necessary. The random-based excitation event recognizes the presence of the Nastran residual vectors and adds their static contributions to the normal modes in the random solution. Now, the output request must be defined. You can request different types of results and formats at once. First, request peak acceleration contours for all the nodes in the FEM, as well as acceleration power spectral density plots for the nodes in the predefined ACCE group. Enable failure metrics and request stress margins of safety. Set the safety factor to 2.5. The code will compute peak von Mises stresses that correspond to the desired confidence level, multiply them by the safety factor, and then compare them to the yield strength that was exported to the Nastran results file. Enable composite failure metrics and request stress margins of safety. Set the safety factor to 2.0. The random-based excitation event will compute peak ply stresses that correspond to the desired confidence level, multiply them by the safety factor, and then combine them, along with the stress limits in the supported failure equations. You can define the acceleration power spectral density function that will be applied at the base of the spacecraft, or you can also load it from an existing file. In the XY function navigator, load an existing AFU file called spacecraft-notched.afu. Next, go back to the Simulation Navigator to the Random Based Excitation Events Excitations node. Define a new translational nodal excitation. Enable the X degree of freedom and select the notched function. Let's plot the acceleration PSD versus frequency function, which is defined from 10 to 100 Hz. The power spectral density was reduced at key modes or notched to avoid over-exciting the spacecraft. Notice breakpoints at 15 and 40 Hz. Edit the random based excitation output request. As the solver may not plot responses at the exact breakpoint frequencies, we add them in the additional frequencies group of the dialog. Solve the random based excitation event. The solution is calculated quickly, in about 1 minute. The solver is parallelized and uses as many threads as possible. The log file shows that 8 threads were used in the solution. Let's look at the contour results first. Load the peak acceleration in the X direction. Edit the post view and set the edges to feature. Then set the units of the results to Gs. The peak acceleration of 197 g occurs at the tip of the antenna feed. This is the maximum acceleration response in the x-axis. Next, load the peak acceleration magnitude. This is the peak phase correlated acceleration magnitude response, which is 244 g, and it occurs at the tip of the solar array. Then load the peak von Mises stresses. On the Results tab, set the shell and the beam location to maximum. The maximum stress is about 1785 megapascals, which is quite large. To assess the stress magnitude, it is also very convenient to look at the margin of safety results. Load the peak margin of safety. Edit the post view and under Legend, click Invert Spectrum, set the extremes to specified, maximum to 10, and the overflow to shaded. You can see that the minimum margin of safety is a negative value, which means that the stresses are too high in the many red regions in the model. This indicates that the input function notching was not successful. Lastly, let's look at the peak ply margin of safety for ply 1. Using Edit in Graphics, edit the color bar to reset the legend extremes. A few areas of the solar arrays have a negative margin of safety, which again indicates that the stresses are too high. Click on Return to Model to go back to the Simulation Navigator. Next, let's review the power spectral density results. These are loaded in the Function Navigator. Right-click Power Spectral Density Acceleration Subcase 1 and click Information. There are 72 functions, 6 for each of the 12 nodes in the group we selected in the Output Request dialog. There are 3 functions for the translational XYZ PSDs and 3 for the rotational PSDs. Any of these functions can be plotted as follows. Right-click a result, click Plot XY and select the main window as the viewport. For the translational results, the y-axis units can be changed to Gs by double-clicking on the y-axis values. Multiple PSDs can be overlaid by shift selecting them. In this tutorial, we showed you how to perform a random based excitation simulation of a spacecraft finite element model using SimCenter 3D Response Dynamics. we used a random-based excitation event that is more than 100 times faster than the competition. We validated the notching of the input PST function by reviewing von Mises stresses, stress margins of safety, and acceleration contours. We also looked at the PST function results. SimCenter 3D Response Dynamics also supports transient, harmonic, and shock simulation, allowing you to create simple and complex input functions by using dedicated function tools. Thank you for watching and have a great day.